Then the system itself has a hydraulic design. And we can lose a lot of head pressure through a system where there are flaws in the hydraulic design, where we run too small a pipe for the flow characteristics that we are requiring of the system. Simply by increasing the size of the pipe, we will increase flow. We will also reduce friction for a given flow as we increase the size of the pipe. So that can be one of the solutions to a better system, is to upsize the components. Now, that increases the capital cost, but it will reduce your operating cost. It will certainly increase your system efficiency. Another thing is the type of material we choose in the pipe. We can choose steel pipe with no lining at all, and we know that as it rusts, it's going to get more and more and more corroded inside, more turbulence is created, and our friction increases over time, and the system gets worse and worse and worse. The end pressures out at the sprinkler heads are going to drop because we're consuming more losses and friction. Now we can, instead of using steel, we could use mortar lining on that steel. Then it's going to be consistent through the life of that system at that point, because that mortar lining does not deteriorate. So we're going to have the same resistance the first day we use the system that we did the 50th year we used the system. We could choose PVC pipe. Same scenario there. It's not going to change its friction characteristics over time. We could go in 20, 30, 40, 50 years later, we're going to have the same friction loss characteristics that we had the first day we used it. Not so with bare steel, because we know it's going to, over time, get worse and worse and worse. And interestingly, the bare steel will even start to create barnacles on it. It'll start to build nodules on the internal surface, and the minerals will start to build internally, and the pipe starts getting smaller and smaller and smaller inside diameter. And that just makes it harder and harder to jam that water through it. Therefore, we lose more and more to friction loss, and our system pressure is going to drop out at the far end. The valves we choose can have a huge effect on the solutions that we get. We can take a globe style valve versus an angle style valve, for example. We can take this valve and it can work as a globe valve. Water can come in this way and exit this way. Well, it looks like it just goes straight through the valve, but it doesn't. It comes in, it has to go down, turn sideways, come up through the middle of the core of this valve, and then gather at the top and exit out the other side. It's called a globe style valve. A tremendous amount of friction loss within a globe style valve. Now we can choose the other alternative, and that's to bring it in as an angle valve. Have the water come up through the bottom of this valve. We can change the way this operates. See which way my arrow is on it. There it is. We can bring it up here and shoot it out that way and cap this side. Now we've made it an angle valve. Now the water, all it has to do is come up, gather in the top of the valve, and turn sideways. So it has to make half as many physical turns. And by making half as many physical turns, it's going to lose approximately half the pressure that the globe style, as if we brought it through this way, is going to lose. Now, the reason that they opted to design the globe style is so that you can run it in line. And so it would allow you to run it straight through. So if you have the plumbing coming straight across without changing the elevation of the piping, you can run it right through the system. And so it's a convenience factor. But in the meantime, you're going to lose, and this is pretty typical of turf. Most of these turf globe style valves are going to lose in the neighborhood of 3 to 4 psi as the water flows through them. And the angle style is going to lose somewhere around 1 to 2 psi as water flows through them. So we can see here with the angle valve, it just comes straight up through the center, bottom feeding, right into that port. All it has to do is collect up here, pull this piece out, collects in this area and then exits right out here. So you see there is quite a bit of turbulence. It has to come up, it gets stopped at the top, it has to flower around the outsides and re-accumulate on this port coming out this way. But it only has to make one turn. It has to come up, hits that top, goes around the top part here, collects in this area, comes back out and exits this way. Now, if we change that flow and make it come in from the side, let's look and see what happens. Now it comes in from the side. It has to turn now 90 degrees right at this point and come up into the center of the valve, then gather, then collect, and go back out the port that way. So it had one extra turn that cost you double the resistance within the valve itself. And so that's the disadvantage of a globe-style valve. But it's very effective to use as an electric operating functioning valve. So we kind of like the idea of the concept of the globe style or the angle style valve as far as convenience is concerned in the field. But they do consume quite a bit of energy. Now if you have that valve on your home lawn system and you got 60 psi like the city of Walla Walla delivers, and your sprinkler system only wants 45 to 50 psi maximum pressure, that's not an issue. You got to eat up some pressure anyhow because you're always getting too much. But if this is on an agricultural scenario where you don't want to be adding more horsepower to your pump because of all of the fittings that create more resistance to flow, it just starts costing you horsepower out in the field. And so you try to go to the most efficient type valve that you can find. So then you'd want to use that as an angle valve. You would automatically choose to plumb it so that it would operate as an angle valve instead of a globe. And the size of the valves makes a difference too. You know, how big of a valve do you put in? By putting in a smaller valve, we can save a lot of money as on the front end of the system, the capital expense of the system. But if we put a bigger valve in, it's going to cost us more money, but it's going to have less friction loss. So we have some economic trade-offs in that regard. Do we want to save money now or do we want to save money later? And an economic evaluation can be made of that to determine which is the most efficient over time. The only problem whenever you go into these economic evaluations, you're guessing. What is the price of money going to be? You know, what's the interest rate going to be next year or 10 years from now? What's the price of energy going to be 10 years from now? Who knows what electricity will cost in the year 2010 versus 1998? It might stay the same. It might be 4 times as much. None of us has a clue what's going to happen to the price of electricity. So we're really guessing a lot when we make economic choices. We're really speculating what's going to happen to the price of money and energy in our industry. And then we don't know what new products are going to come down the line that might make these obsolete also within that particular system.